do. We'll put a couple of nice examples that you can find by going to Piazza, and at these examples you see already that the billboard is actually much larger billboard, but it has a lot of transparent pixels. You have more transparent pixel in the other examples that we could have cleaned maybe a bit more. Yeah. So that's a GIF file. You have an example of how to create GIF files out of which. Stop it. The cat, the projector, slaughter the quality here. It looks much better on the monitor. You see that the cat mostly is non-transparent, while the pixels around the cat are mostly transparent, beside a few artifacts, these clouds that you see over here. But they have transparency of have alpha equal 1, meaning transparency equals 0 or opacity equal 1. People? Questions? Yeah.
Is there diffuse shading on the billboards? It doesn't look like.
Shading on the billboard you don't need to do. If we did shading, I cannot say, but yeah, billboard you don't need shading. Spheres that you definitely need. Remember, spheres you need diffuse shading, but not specular. Today we'll study how to do specular, by the way, but in the homework, it will make it to the next homework. In the next homeworks, we might already go to WebGL and do it all GPU based. Well, the basic idea behind ray tracing in WebGL would be with GPUs will be I'm using the Z buffer to find out for each pixel in my image. I'll use the hardware to find for each pixel of my image to see what falls out of all the things, what falls inside each pixel. And that's the GPU, the depth buffer, can do extremely fast. That's what it's made for. What it doesn't necessarily help me to do is to find how much light falls on it, any secondary path that goes from it, which we can still do in parallel, but will require a bit more programming in WebGL. So I'm quite tempted to do it already in Homework 3. There is a course in graphics in University of Utah, which is a big mecca of that. There is a link that I gave you for the YouTube version, and I like the idea over there that we are using their GPUs as early as possible. Anyway, questions? Homework 2? Everybody? Homework 1, I guess. Nobody complained, nobody came to office hours, nobody had issues. So I guess between having a very talented group, yeah.
When will we get the grades for homework 1?
These days we'll this. So we are aiming for a week, 10 days. Usually, of course, I'm tearing between having extensions, which I usually tend to be more timely in the grading. There is two outcomes to each other, but for homework 2, only one person needed an extension, and it was for a couple of days, so I don't have any excuses for not having the grades out already. But yes, we talked about it with Amir, and in the next, I think, days, we're only, yeah.
Can we have a small extension for homework 2?
Of course. Do you want to specify how much, or should I just what? If you have a the answer is sure, and we also need to start thinking about the midterm, where exactly we want it, where my philosophy usually, people took courses with me, trying to let you know when in other courses you have strict deadline, and we'll pick the midterm accordingly, so you'll have minimum conflict with others. So still don't need the answer, but yeah, it will cover probably everything that maybe the material will be the beginning of March and then a bit after that. So the big question would be before, after break. All questions to be declared. Okay, JSON files, you saw the difference was that we wanted to, comparing to the previous years, among others, is that you want to do some very basic animation. Why did I wanted to introduce animation? Because if you just look at the figure, it consists of multiple things, and from a single frame, it's extremely hard to know what's happening in the frame. So it's frustrated for you of not being happy to show it. It's frustrated for us to grade it. Once you have a few frames, then, like in the example that I showed you, the 3D structure jumps when anything moves, like the camera moves. So instead of you have the spec, instead of having a unique location of I and unique direction of up, you have beginning of end of location of up, and maybe other parameters, at least the ones that I remember right now, location of I and location of up, beginning at the end, and then you're generating multiple frames in between. Complexity-wise, if you can generate one frame, you can generate quite a few, and then you collect them using a GIF, and that's it. So it doesn't make the homework any harder. Amir added a little example that shows you how to do GIF. And I mentioned that my recommendation start when the resolution of the camera is really low, because it will run slowly, even for single frame. Even without Specular, it will run slowly, so start to see that you're in the right direction. And expect that your first while it will be upside down, left, right. Everything here will be completely off. Your pixels will be off by half a pixel. You'll start from the exact beginning of the leftmost point of the image plane instead of the image plane boundary plus half a pixel. All these little artifacts that either just ignore and will ignore, we don't care that much, or handle it when everything else is smooth. When do we on the right slide. Wrong set of slides, sorry. Okay. Last meeting talked about the moon paradox. And the talked about a diffuse reflection in general. Now let's start to speak about specular. And to define what is specular reflection, we'll start by saying how does a perfect mirror behave? It's much easier to understand what is specular shading when, with respect to, or when we know how perfect mirror behaves. So perfect mirror, there is a light source. The light source is omnidirectional. It sends direction of lights to all over the place. Omnidirectional. The viewer right here will see the light source reflected in the mirror, but only at one specific point, a single point. And what's so special about this point? The angle of the reflection equals to the angle that it hits the mirror. This angle equals to this angle. Or, equivalently, if I shoot a normal from the surface up, assume that it's smooth enough so I can have a normal and well defined. If I shoot the normal up, then the angle between the normal and the direction of the incoming light equals to the direction from the normal to the outcoming light. In particular, these two vectors are coplanar, and these two angles are the same. Remind you all, standard pull trick, you want to ask how do I shoot the cue ball so it will, what I want to hit, I want to hit B1, I want to aim from B2, and I want to shoot B2 so that my B1 will fall into this hole. How do I do it? You all know it, right? There is various balls over here, so from B2 I cannot shoot B2 to hit B1 directly. I want to bounce it through the edge of the pool table. How do I do the mental trick of deciding at which direction should B2 be hit? Nobody? Come on. I'll try to draw it better. Pool table. B2 wants to get into this hole. B1 is a black ball, that's what you're hitting. So you have to get B1 to some point over here. Problem, various other balls are arranged all the way in between. The path that B1 will do is to hit some point and be reflected from the edge of the ball, and then hit B2. But where should I aim when I hit B1? Answer, let's take B1, let's take B2, look at this height, age. Draw the same direction, the same age in the same direction, and imagine a imaginary copy of B2 right here outside the table. And now look at B1, the cue ball that you hit, and aim it so B1 is trying to hit the direction of B2 prime, which would mean that it will reflect from from the edge of the table, and if the table is of high enough quality, this angle alpha equals to alpha, and you'll hit B2, right? This imaginary of the reflection, and we'll do this imaginary of reflection when we'll talk, for example, about mirrors that we want to generate a scene for them. Like we will have homeworks where you want to create 3D scenes using your GPU, but in your scene you have a mirror that shows other part of the window. So I'll imagine virtual camera that is on the other side of the room and will show me what the camera will see. Homeworks that will come up much later. And then once we have the other camera, we will use texture and just place it as a poster, as a, dare I say, billboard in the big scene that is generated. So we will have a few passes of GPU pass, depth order path, depending on to generate a reflection with the camera. Going to be a very cool trick. Back to our specular reflection. Where do we see the reflection of the light if these two angles are the same? Okay, that's the only point that the viewer sees the reflection of the light when it is a perfect mirror. Specular will not assume perfect mirror, but will assume that we start from a perfect mirror and then correct it. Okay. Distance D over here to the edge of the mirror, the edge of the table, distance D over here to create this mirror. Well, you all know how mirror works now. Okay. So the same thing with the eye, lamp, mirror. Where do I see the reflection of the lamp? Exactly at the single point at which the eye, if I create a normal, the angle D between D and the normal equals to the angle between the normal and the direction to the reflection. That's if it's very good mirror. How it's related to the specular reflection? Because the specular shading, the center or the maximum area will be exactly where I would have seen the reflection of the light had this sphere be a perfect mirror. It was a convoluted sentence, so I'll repeat it. If this green ball would have been a perfect mirror, then I will see the light at one particular point, assuming that it's a light source, a sun. Just one light source that I see its reflection right here. That is the center of the specular spot. And the way that you are doing a specular shading is starting from the specular spot, but then allows some other freedom of angle that indicates how much light is reflected as a function of this angle. Okay, and same for generating the reflection of the ball, including the reflection of the specular spot in this shiny window, shiny table. Okay, so what are we doing in ray tracing? For each pixel in the image plane, what you are already doing in homework 2, trace a ray D from the eye via the pixel till it hits the object. If this object is a mirror, then I'll just start my ray tracing again, but from this point further. Not in homework 2, maybe in later homeworks, if you'll have mirrors. Okay, just use the same recursive call to the what's the first object that I hit, but now my eye is not right here, the camera is not right here, the source of the camera is right here. So you need it both to work with mirrors as well as to generate specular shading. Okay, how can I find R, this vector R? So in general, I don't know even what is this point that I hit necessarily this way that I hit, but in general, if you're thinking about homework 2, homework 3, you had these multiple pixels in the image plane that I'm imagining right here. For each one of them, I picked a direction D, and D turns out to be a vector, and that's the hitting point. So I know what is a hitting point, and I know what is D. I need to find R. And there is a cute trick that tells me how to generate R quickly. So plane, you want the normal to the mirror to the surface. You'll also need it for the specular reflection. Whatever it is, find the normal. If the surface is a billboard, what's its normal? Just to see that we are in the same page. The normal points toward you. How do I calculate the normal that you do need for homework 2?
Cross product of the left and top edge.
Take this vector, take this vector, sometimes called U and V, take the cross product that point toward the normal, which one do I take? U cross V or V cross U? V cross U, I think. From V to U, I think that's my normal go to the opposite direction. No? From U to V, again, think about the screws that you're putting right here. If you are rotating it in counterclockwise, then from V to U. So N that points toward you, if that's your billboard, would be U cross product V. Am I right? That's you. I know my handwriting today is. So that's how I find the normal to a billboard. How do I find the normal to a sphere? We talked about this one as well. My way, I find the hitting point, center of the sphere. Q is the hitting point. What is a normal? Or what's the direction of the normal? I don't commit about its length. What's the direction of the normal? And at this point is Q minus C. At least in the direction. Don't commit that it's unit length. Okay, so we know what is D, we know what is M. Claim R is take D minus 2 times D times N, that's a scalar, times N once again. Let's prove it, it's cute. Okay, a very simple calculation that tells you what is a new vector, where if you're generating a new ray, what is the direction of this ray as a function of the normal and a function of the ray that hits the surface. Why is true? So let's assume that the normal is just 0, 1. Normal is a y vector, and my surface is perfectly horizontal, at least locally it's horizontal. Locally, I mean, my surface might be a sphere, but looking at the top of the sphere, close enough. It's just a normal. Okay? Normal points vertically upward. Now, D as a vector has 2 components. There is a dx, thinking about the velocity. Dx is how fast you are moving toward the surface. Dx is your horizontal velocity, how fast you are moving from left to right. Dy is your velocity on the y direction, how fast are you moving downward. Both fixed speed, no acceleration, like here. So given that set is D, that the components of D are dx and d dot y. And again, I'm assuming that it's no. I assume that my surface is horizontal. That the mirror that it's normal. Please tell me what is R. Component of R, it has X value, its Y value, but these two guys, how will they relate to each other? Can you generate the components of R in this term? Yeah, yes sir, it's end. And you're shooting a basketball, basically, and this basketball has perfect bouncing. It doesn't lose any energy once it's hit.
No, are we talking about the direction or for R is the direction or so we should have the same dx, same x as d, and then it's the negative of
Shooting the basketball, it has some horizontal speed. It hits the ground, it starts balancing, but its horizontal speed stays exactly the same. So the horizontal speed is just dx. And it's a perfectly bouncing ball. I didn't lose any energy. So what should be the vertical velocity?
negative dy.
And negative dy, right? Instead of going downward, going upward. At the very same velocity. If you all agree to this formula, then the rest is just formality. So they have the same x value, the same horizontal speed, but opposite y value, r and d. So r of x is dx, and r of y is minus dy. And let's write r of y as, in a very strange way, r of y plus minus 2 times r of y. Very strange way to write r of y. But what is d vector times n? And here I'll assume that n is both normal to the direction and have unit length. So it's a projection of d on the vector n. This number is nothing but from these guys. It's just again, think about it as x is the x vector, y points up, is a y vector, points upward. So n is just a y vector. And d times y, this projection is just d dot y. Agree? I don't care about dx, I care about the length of this vector. The length of this vector, d projected on the unit vector n, tells me what is its y coordinate. So this is a dy, and now we understand this formula. The r of y, written in this very strange way, is just r of y minus 2 times n dot product r. Yeah?
So is the reason why we're doing this the kind of convoluted way instead of just writing negative ry? Is that just because
Excellent question. Why are we doing it in such a convoluted way? Because dot product is something that our hardware really likes. Calculating angles is something that we all hate. I don't want to know what is theta. It's a great question. I don't want to calculate what is theta. I know that there is a vector that comes and hits my surface at some point. I can calculate the normal. I'll have to calculate the normal. But I really don't want to calculate, especially not in 3D, at which direction R goes by, let's rotate this angle by some angle, because that will be different for different points. I want to create the whole image a lot of ways that hits lots of objects, and for each one of them I need to do the same gymnastic. So here in this formula I never need to know what is theta, at which angle did I come. Right? I just need to know at which direction did I come from and what is the normal. And then it's just dot product that our hardware likes. Okay, so we have R times Y. So D times N is D times N, or N times D, is what we need to subtract. Times N is a zero vector. I multiply this constant times N. So far, I had the length of the projection multiplied by N once again, bring me to a vector at this point. And all I need to do is to say R equal D minus this new vector that I just took. And what happens? What used to be the vertical speed now added to be the same magnitude of the vertical speed, just at the opposite direction. And the horizontal speed is unchanged. Okay, if you happen to have, last year, you had to have mirror spheres, now you can compute with this formula how are you doing ray tracing from the eye. If you have a mirror sphere, each time once your ray hits the sphere and it turns out to be a mirror sphere, which is JSON tells you, compute the intersection point, compute the normal, normalize it to be a unit length, do our little formula to compute the direction of the ray that emerges from the mirror sphere, and ask what is the color of the first object that this ray hits. Because if this ray hits a green bolt, then the color that I assign to this pixel is green. Okay, specular reflection. So we are not going to mimic the specular reflection in terms of the physics. Diffuse reflection, the cosine was exactly what happened. There is no approximation out there. That's just because that's how much 1 over cosine tells me a surface of unit length that is directed towards the sun. If I change it to be at angle theta, the same amount of light now needs to cover a surface that is larger by 1 over cosine. Exactly, no approximation. Specular reflection way to generate the specular reflection is just an approximation. Why are we using it? Because it looks good enough for most materials. So what do we say? Here's the sun. It hits the mirror, sphere or not sphere, doesn't matter. And here is the direction of the reflection, exactly. That exactly is the direction of the reflection. That is incoming angle with respect to the normal equal to the outcoming angle with respect to the normal. Or if I put the tangent surface, then this angle equals to this angle. That's exactly the direction that I would see the sun had it been a perfect mirror. But it's not a perfect mirror, it's a shiny object. Plastic shiny ball. So I will see the specular reflection definitely if my eye is exactly an R. That's where I see the sun in its most intense, as intense as it gets, maximum intensity. But if I'm moving the viewer by some small angle alpha, hard to see, it's alpha over here, some small angle alpha over here, then as long as alpha is small enough, you'll still see the reflection of the sun, pretty much. As long as alpha is small enough. What is alpha again? I'm just repeating the description. This is perfect reflection, R, that's the direction D from the sun, and this angle is alpha. And if you think about Phong surface, if you think about shiny surface like the table, the top of your laptop, you will see most of the reflection as long as this alpha is small enough. What do I mean small? I can set a threshold of yes and no, but that doesn't look good. Instead, we already made a habit to work with cosine, because cosine will boil down to be just vector multiplication, just dot product. So we need to come up with one more coefficient, which would, surprise, surprise, call the Phong exponent. And I warn you again, Phong will describe a few things in this course. So that's Phong approximation of specular reflection, of specular shading. So what is a intensity that is reflected? I'm looking at alpha. I want to have the maximum intensity when alpha is 0. Alpha is 0, meaning that it's perfect reflection. I just watch the direction of the sun as if it's perfect mirror. Alpha is 0, what cosine of 0 is 1, meaning I'll have the maximum intensity at this case. I'm only going to compute some number here that will be a reflection coefficient and multiply it by how much light is actually coming to the sphere. It will worth mentioning the sphere. We are talking about this sphere over here. You see the specular spot? The middle of the specular spot is a point that I see the reflection of the light as if it is a perfect mirror. But as I'm moving away from the center of the specular spot, the intensity is decreasing, maybe faster, maybe slower. Faster or slower is exactly where the Phong exponent helps us to determine fast or slow decrease. And why do I stop seeing the specular spot is because this alpha, as I'm moving, instead of watching the center of the sphere, I'm watching the point that is not exactly the center of the, instead of watching the center of the spot, I'm watching a point that is just slightly outside, slightly outside. That is, on the surface, I'm asking what is the reflection here and here and here, at which the normals are very small, alpha is very small, but still changes a bit. From being a 0, it increased by some amount. We all agree the normal at the center is different than the normal of a point just near it. So, Phong says cosine. Why do I like the cosine here? Because it behaves nicely. I can compute it quickly. I'll take cosine of alpha. When alpha is 0, perfect mirror, perfect reflection, I'm just standing in the right place, it will be 1. And if it's 1 to the power of m, it still be 1. But if alpha is different than 0, but very close to 0, then cosine of this number, what does cosine looks like? Start at 0, it will start from 1, and it goes down quite quickly. If alpha is right here, or alpha is right here, then the cosine is less than 1, and the cosine to the power of m will be much smaller. Remember, less than 1 times less than 1 times less than 1. And usually this coefficient will be somewhere between 5 and 40. These are the typical values. Okay, everybody understand? I compute alpha, and then I'll show you how to do everything without computing alpha. But at the moment, I compute alpha, this angle over here, compute its cosine, decide about how shiny the material is that helps me determine what is m. And now m is fixed for this surface, and the reflected value will be cosine of alpha to the power m. Let's see how it looks. So, okay. Probably time for a new slide for here. And here m, instead of m, we'll call it p, the exponent, still the Phong exponent. And let's think about it. If p is 1, if the Phong exponent is 1, then the intensity that is reflected is cosine alpha. Cosine to the power of 1, meaning that even if you're not exactly over here, if you can see, you're not exactly theta at alpha equals 0, but you're very close enough, then cosine is still very close to 1, meaning that you can walk away from the center quite a bit and still get almost all the intensity. The intensity doesn't decrease doesn't decrease rapidly. But that is p equal 1. What happens when I start increasing p? Then cosine of 0.9, if the cosine is 0.9, then here I'll get 90% of the area of the intensity. Well, here I'll get 90 to the power of 10, bringing me very, very close to 0, meaning that unless I'm just looking at the exact point of perfect reflection, I'm getting no specular spot. Make sense? As p, the Phong exponent increases, the size of the specular spot becoming smaller and smaller, centered around the point of the perfect mirror. Everybody's good? All because you have cosine of alpha to the power of, in this slide, it's p, the Phong exponent. In the previous slide, it was m. This was also the Phong exponent. But p equals 0, p equal 1 will make it looks like so, while p equal 10 will make it still start at 1, but drop to 0 much more rapidly, meaning that the moment that alpha is anything but 0, you'll get a very fast drop. Now, what is Ks? That's less interesting. That just says that in OpenGL, you can specify 3 sets of coefficients for the surface. One for the ambient light, red, green, blue, how it reflects, irrespective of the direction. One for the diffuse shading, another set of 3 coefficients, RGB. And finally, one for the surface itself, that of course more reflective is important than less reflective. Something that definitely worth explaining is that we can show assign color to it, and we all can assign that the color that is coming is not white, but if the light that illuminates the surface is white, then I don't care one bit what is the color of the ball. The ball can be of any color. The specular spot will work the same way for all the frequencies of light that illuminate it, meaning that if the light that hits it is white, it will be a white specular spot, even if the sphere itself is blue. But we saw the example last class, let's repeat it. Override. So, shiny shape in 3D. Here are ambient light only. You just know what is its silhouette, but not what is its three-dimensional structure. The moment that I introduce diffuse light, then I can ask what are the normals to each point. Well, I don't know exactly the direction of the normal, but I know a lot about the normals, and actually there are techniques of 3D reconstruction that says if my surface is nice enough and I just have one source of light, then I can do 3D reconstruction just based on the diffuse effect. There is a lot of 3D structures that is coming from it, plus assuming convexity, plus assuming that it's somehow smooth, but of course I can cheat. Create the same surface, create a different shape in 3D that will look the same with the diffuse light. Let's now calculate the specular spots, add the specular spots, and it looks so much better, including seeing the specular spot whites despite it being blue, exactly at the point of the specular of where I would see the perfect reflection. And once again, if the viewer moves, the diffuse light doesn't care, the specular one does care. The specular spots will move according to the viewer. So while it's not requirement for homework 2, I think that it will look better and you'll be prouder with your work if you do editing. Okay, so we have this alpha that we can calculate, and once we have alpha, we have the cosine to the power of p. P is decided that we wanted about how large or small the coefficient is, except that we said that we hate calculating angles exactly. So Fong, or Bing Fong, came up with a hack. And I'm not going to tell you that it's exactly the same thing, but it looks good enough. What they said, you don't want really to calculate alpha over there. Instead, calculate this new vector age. What is age? Vector to the I plus vector to the sun. Take these two vectors and normalize it. Vector to the I and vector to the sun, and just make it a unit vector. And what is the direction of age? What is the direction of age with a perfect reflection? Here I have R and the reflection and the direction to the viewer a bit separated, but let's assume that alpha is 0. So this vector is both R and the perfect reflection, and at the same time it is also the direction to the viewer, what we called over there V. And please be so kind to tell me what is age in this case. Let's move to normal mirror, flat mirror. Here is the light that is coming at angle beta. Here the light reflected at angle beta. This is the sun. This is D. And this is a perfect direction to the viewer V, which is also perfect reflection R. And my question is, where is, if you sum up both these vectors, which vector are you getting? Yeah.
You get the normal to the surface.
Excellent. that I'm not committing about the length of this vector, that's depending on this angle beta. Even if this is one, and if this is unit length and this is unit length, this vector can be shorter or longer, I don't care. But I care which direction does it point to, and if it's perfect reflection, then this is nothing but n. At least up to a constant, points in the same direction of n. And if the viewer moves a bit, so now this is R, but this is V, then what happened, the direction to the viewer, what happened to this edge? Edge is now not the normal, but still very close to the normal. If this angle beta is small, then this angle gamma, which if I remember, let's call it delta, which is about beta over 2, is also very small. Yeah.
Oh, sorry, I was just doing.
Yeah, one is half of the other, and it's a heck. It doesn't need to be the same. It needs to be the more the viewer is out of the perfect reflection. Remember, it doesn't make sense to talk about the perfect reflection if it's a flat surface. That's why I need a sphere. There is a point of the sphere, no matter whether the viewer and the sun, there is a point on the sphere at which you have the perfect reflection, perfect direction, and if you move from this point just by tiny bit, then now the perfect reflection and the direction to the viewer are different than each other. And there is some gap beta between them. And at the same time, there is also gap delta between the normal and this average of H and L. And again, I'm not trying to convince you that it's the same number or even that one is half the other. I'm just trying to give you the feeling that quantitatively, if the viewer, I picked a point at which I have the perfect reflection to the sun, then H would be the normal. And if I diverge from this point a bit, then H is slightly diverging from the direction of the normal. If you believe me, up to this point, that's all we need. Because now the heck says you have the fun component, you want to compute cosine. Instead, earlier I told you to compute cosine of alpha over here, direction to the viewer. Instead, I'll tell you compute cosine of delta. It still behaves roughly the same graph. Why? Because I want to use dot product as much as I can. So at the end of the story, V is something that you can compute, direction to the viewer, direction to the camera. L is something that you can compute, direction to the light, to the sun. Take their average, normalize. You need to know the normal at this point, sphere or billboard or whichever, doesn't matter. Decide about the Phong coefficients. You just say I want it very shiny or less shiny. P, as I said, between 5 and 40. Usually it looks good. And the Phong effect, the Phong simulation of the specular effect would be intensity of the light that is coming. Again, in RGB, if you have the whole channel, if it's the sun, just you have maximum percent of RGB, just white light, times n dot product H, all of it to the power of P. So you'll get a much quicker decay if you want. So the specular spot will be much smaller. And since we already saw this trick, since this number can be negative, I don't want to decrease from the intensity, to subtract from it anything. I'll just take the maximum of 0 and this value, multiply by how much I want to see the effect of the specular reflection. You can assign a coefficient if you want, if not our default in OpenGL, WebGL. That would be the specular reflection. Right? And when we are saying that we are adding the contribution from all the sources of light, that's exactly what you see right here. For every pixel that I see, I just sum up the contribution from all the sources of light. There is more than one sum over here, one sources of light, and from all the types of shading that I have, ambient plus diffuse plus specular, just per every pixel, sum up all these terms. So sum up, look at the ambient reflection. The intensity will be the ambient reflection, plus for every source of light, ask how much is source of light adds in terms of the diffuse, that just cares about the cosine to the between the light and the normal, plus the add to it the specular that now takes the direction to the viewer into the game. Sum it all up in RGB. That's what you show for this pixel. And of course, you are making sure that these values that you are getting in this expression can be above the 250, 256, 256, 256. So you either limit it to 256 or you are using a dynamic range that we'll study later in the course to show more contrast between darker parts and highly illuminated parts. But that's it. Let's summarize our three shading effects. Questions? Everybody's good with the diffuse? And again, I'm not trying to argue I showed some semi-proofs. What I did not show is why the diffuse that you see appearing on shiny surfaces is mimicked or behave according to the Phong heuristic. The Phong heuristic is exactly as I said. It's heuristic. It looks similar enough for surfaces that lack directionality. But if it's a metal thing that I specifically hand scrape it or hand brush it, and there is some directionality that comes from the how did I painted it, then we need a BRDF function that is one step higher in the complexity. Then I cannot treat the surface as isotropic, that all directions are equally good. Yeah.
So you said that those coefficients, we have different ones for RG and B, but I'm guessing that they would be continuous with color. How accurate is do we only need to sample at those like three colors? We shoot rays of each color to shade the RG and B values?
I shoot one way, and I assume that I put a blue lamp, so from every surface, so there is a single blue lamp. So what will be reflected for each point of each surface is just the blue light, because there is no green or red. And now, depending on the color of the surface, I'm asking how much blue are there. OpenGL lets you pick for every source of light. OpenGL, when you describe the scene, as well as Blender, as well as many other such engines, let you specify what are the direction of the light, what are the sources of the light, what's the RGB value of each source of light, omnidirectional or directional source of light, as well as specifying for each surface at least these three sets of parameters: the diffuse, specular, and ambient. For each one, how much is reflected from the light to the RG and B. Do you have to use all of them? Luckily, no. You can leave them as default, and that's just fine for most C. But it starts to be quite dramatic if you want to add, for example, in I have it. Where do you see dramatic effect is you see the reflection of the table of the blue sphere. So that is specular. Reflection of the blue sphere. In other words, there is blue light that is reflected from this sphere and hits this surface. So had the surface had a color, then this accurate reflection of the spheres would have looked differently, because now the light that hits the surface is not white, has a clear color depending on light that bounces from which surface it is. We'll actually get to it either now or next class when we'll talk about distributed ray tracing. Okay, simple ray tracing, just summing up what we said. Overall, you have from all the surfaces, the color at each point is the color so far, plus if I hit the surface, how much do I get from each source of light per the diffuse, n times L, good midterm question, n times L always stands for the diffuse because just cosine there. Direction to the surface and direction to the light, the same diffuse effect, plus here there is an HI which takes into account, as we said, the average to the viewer and the average to the source of light. And I sum it up to all the sources of light. And that's the ray tracing, that's essentially what I'm assigned for each pixel. And obviously, if all I have is a single CPU and multiple sources of light, and I want all the effects, including the specular, then a ray that comes per a single pixel in the image plane that hits the surface. Now I want to see what is the direction of to the light, to compute both of them, and possibly what is the direction to the viewer, if needed, because all of them are in the specular effect. So things are harder. Let's talk about Snell law. It goes together. I could have requested, could have avoided. Snell law goes well with the diffuse effect. Light that hits a surface with different medium coefficient, let's say glass or let's say glass or quartz, change its direction, continue inside the quartz or the glass in a straight line, hits another boundary, change its direction again, and continues. And that's Snell law. Where do you need it in graphics? Because you want to show lenses or crystal ball in your sphere, in your scene, sorry. You have a crystal ball or a lens that appears in your scene, and you want to show the scene as it is seen via the lens. So, show me hands. How many of you have studied Snell law? Okay. So you in optics, you in high?
I took physics 2 in college.
Okay, and the rest there was random. So we are talking about the frontier of the wave. The waves, the sinus, if you think about the sinus, the wave moving locally, and it is moving in a constant depth pool, and now you hit an edge where the pool becomes much deeper, and this frontier of the waves suddenly changes its direction. There are better examples shown, and it's also much clearer seen over here, but once again, that's the direction where the wave in the water moves, and if I just dropped a paddle into the water and the wave propagates, it will create co-circular wave where the first wave moves somehow locally, it moves as a straight line, looking at it at a small enough region, and suddenly the straight line changes direction. Now this is the direction that a wave propagates into. And Snell observed a very simple part. So there is a speed of light in every material. Every material will have the speed of light inside. This material, let's say, it is faster in air, slower in water. So N, the medium coefficient of water, will be roughly 1.3. And outside, when my light coming from outside and hit the surface of the water, that's its speed of light. We'll think about its coefficient as 1. Other parts where you'll need this, if I'll use the same homework as homework 6, then you want to use GPUs to simulate when you see the sun illuminating the pool, but the pool has wave in it. You see the reflection of the wave on the bottom of the pool. Some areas of the bottom of the pool has more light, some area has less, and that's as a function of what happens to the surface of the water at this point. And it changes in time as the waves propagate, and you want to ask, how does the light change its direction when it hits the surface of the pool? That was a fun homework that maybe we'll give as the last one. That would be extremely slow on single CPU, but luckily we can do it all in parallel for every pixel of the pool, all at the same time computing how much effect there is from different directions. So if it will be relevant, we'll revisit Snell out there. In the meantime, let's at least know what does Snell tell us. So the direction of the light bounce a light that is coming from the eye, let's think about this, as a source of light hits the surface and reflect to some direction. That's a reflection. Some part of it, depending on the material, also bounce into the material, and this is a refraction. I took accent reduction clinic a few years ago. They offered it in the speech department. I worked on my W's with some success. I can pronounce the difference between weak and weak, sometimes C and C, sometimes. My R is a total disaster and still for many things. If I said something that sounds like W, it probably means that I was trying to say R. So refraction. Refraction in the pool, the straw that suddenly looks broken, the effect in the lens of the camera, or sometimes the direction of the refraction is dramatic enough when it hits the boundary of this fiber material that it is strong enough that the light actually doesn't leave this lens, and it bounces and stays in the lens. And probably tell you stuff that you all know, that if now I'll create from this transparent material a pipe, or a fiber, shoot a ray of light, say a laser, that will hit the bottom, that if this angle is small enough, it will reflect and stays inside the fiber, and will stay inside the fiber, and will continue with direction of the fiber forever and ever, except that it loses some energy when it goes. So that's all behave according to Snell law, and let's compute Snell law. So Snell law said there are two coefficients that you cared about. There is a coefficient of the air, which is 1. There is a coefficient of glass or water, close to each other. Think about the direction, the angle theta between the light and the normal when you enter, and think about phi, the angle that the light continues inside the water, that phi, again, with respect to the normal. That's how the two things behave each other. The nt sinus theta, 1 nt, or sinus theta, the direction, the coefficient outside, is n sinus phi direction outside, so the right n. And the explanation is very simple once I find the GeoGebra. And again, that's beautiful law, and it doesn't really, and it's not any approximation. Here is within time. Here is my wavefront of the light. So my source of light is somewhere here at infinity, going to that's the direction to the sun, and the frontier of the light moves as so, parallel to itself. Both endpoints, P1 and P2, move in the same speed, which is the speed of light in the air. And they are happily continue parallel to each other within time until one of them hits the face of the water. You saw, since I wanted to understand Snell law, I built the GeoGebra for it. I hit the one side of the frontier already hits the water, so it will start moving slower from this point. P2, on the other hand, still is in the air, so it moves much faster. P1 start to move slower, smaller gaps between it. P2 will eventually get into the water, but at the meantime, it moves slower. What happened to the frontier? How come the frontier changed its direction? Well, the frontier is always parallel to the direction, or is always parallel to the direction of the light. So the only way that these 2 points can still be on the frontier is only if the direction of the frontier change its normal. How should it change its normal? It's exactly depending on the speed of light in the two coefficient and this ratio of the sinuses that we saw on the slide. So it's cool because it's very simple law that is not an approximation. So once again, you want to ask from the sun what is the bottom of the pool that this light appears. You need to compute the direction to the normal of the water at this point, compute theta, and from theta you can compute phi. Phi, if you believe this formula and you want to ask what is phi, then phi is, well, you have two sinus, so you are taking the inverse of the sinus of 1 over 1.3 sinus theta. So that's what happened to the sun in its direction to the bottom of the pool. And if it's a viewer that watches the pool at this direction, then what you think that happens here, if you continue it as a straight line, actually happens here because you changed its direction. Except that involved computing phi and theta, 3 more seconds. And we said we don't like to compute angles exactly, so there is a hack to tell us what is this direction. T, this vector, would be dot product of this vector, this vector, direction to the normal, direction to the light, the coefficient n and nt, as we said, 1 if it's 1 and 1.3 if it's like stuff. All in all, it's long and ugly expression, but you only need to multiply vectors by other vectors, and voila, you have the new direction of the light without needing to ever compute what is phi directly. So practically that's what you need to use. And I think that you should all feel thankful for me not proving that this is the same function as before. So that's practically what the graphics book will say. If you need to have the effect of water, or where did we have it? You need to have the effect of water or lenses or anything else. Use this simplification. Get it from Japat, obviously, or whichever, and that's the code that you need. And of course, and confusingly enough, this n are different. That's a coefficient in the air, so that's 1. And this n with boldface is a normal, because if it would be a sinus as in homework 6, because it's wave of the water, then you want to compute the normal at each moment. Okay, thank you.